Yeah, so this is the Gaussian integral for an n-dimensional system. So A is a real symmetric matrix, and J is a real vector. And what we're going to do is build on this Gaussian integral today, and pay special attention to the inverse matrix elements, because they're going to serve the purpose of our green function that we're going to discuss in detail. We've already come across this sort of green function. Basically, I think when I talked about the correlation functions last time, I just told you the result of this Gaussian integration and the relationship between this and the green function when we're calculating expectation values. Today, we're going to explicitly look at expectation values in a bit more detail. And we're building up a toolbox to essentially calculate two-point correlation functions or higher point correlation functions in the 5-4 field theory that we motivated like 2 classes ago before I started writing down all this Gaussian integration stuff. So the thing we're aiming for is, given given a set of variables, this matrix A is calculating expectation values between those variables. So just remember, I'll continue on with this same sort of vector notation now before we go to functional integration again, just to keep everything well defined. So I have n real variables. That's the x's, which are the things that I'll want to calculate the correlation function between. Okay, so big N, I guess. A is a real symmetric matrix. All the eigenvalues are positive. We talked about that last time. And we're going to define expectation values basically in the usual way. So I'll start with the probability distribution. That's weighted by the Gaussian. Okay, that's weighted by a Gaussian function. And we're thinking of like a partition function, like a finite temperature, partition function or something like that, so that we can use this technology to calculate finite temperature expectation values, say, for example. Okay, so I want something that's basically reminding you of a Boltzmann weight. But it's written in terms of these discrete variables. So that's my transpose of that vector. That's the matrix. That's the vector. And I'm normalizing this by what I imagine is the analogy of the partition function. But the partition function for the Gaussian system. And what this is going to turn into as we go on is like Z naught, the partition function for the non-interacting system, right? And this is like the Boltzmann weight that's going to weight all of our various arguments of the expectation values. So most generally, the expectation value of several variables can be written in terms of this. So Okay, so several of my x's. I'll label them with indices I, which is going to get messy. I guess small n. So there's big N real variables, but I'm only interested in like the correlation function between small n of them. Could be 2, could be 1, but let's deal with even numbers in our mind. So what we're doing is now using this p of x, which is normalized by, quote unquote, the partition function to write this thing. So in the usual way, so we integrate over the variables xi1, xi2. Okay, so for any operator, big O, whatever this is how the expectation value is defined. Integral big O, weight, and then normalized by the partition function. Yes, okay. So the way that we calculate this type of expectation value is basically through a trick. It's by generating this integral on top, by differentiating a Gaussian integral that includes terms proportional to these fields or these variables. And we differentiate that expectation value to bring down all those x's. So sometimes called a generating function. I'm going to move over here. So like I say, we can generate this. The repeated differentiation. Of an exponential. So we have to make our exponential include a dummy variable that we're differentiating with respect to, and all those fields that we're interested in. So okay, so this expectation value is generated by taking small n partial derivatives with respect to a variable I'll call j. Because I want it to look like that. Partial j I n. These j's don't occur in the expectation value. So at some point I'm going to set them all to 0 after taking the derivative. Then this thing's acting on basically the numerator. But remember, I want to generate this expectation value by bringing down a bunch of x's from the exponential. So I can rewrite this Gaussian with these extra terms. And I'll just say j dot x. And remember, those t's are just transposes, just to get the dimension of my vector correct. This is a vector. J is a vector. Okay, this is pretty messy. I'm going to drop this notation right away. Right, and j is set to 0 because this thing doesn't occur over there in the exponential. All of this over the Gaussian partition function. Okay, so we'll see explicitly how this differentiation works, but you can imagine just moving it in here and rattling off a bunch of these x's, the ones that you want, you know, the components of this vector that you want right here. So because this derivative doesn't act on this original Gaussian part, I can just rewrite this thing as the derivative well, number one, this thing is actually just what I wrote up here as I. So that's handy. So I can rewrite this as just a derivative in more compact notation. What do I call that? AJ. This should be J set to 0. And so then this thing on the bottom, this Gaussian, is just I, A with J equals 0, right? IA 0. I might have used that notation last time. I forget. Yes, I did. Oh, except I have Y's for all my variables. Damn. Too late now. X's, Y's, whatever. Okay, so I'm taking derivative, but I'm only actually taking derivative of this part with the J. So I can pull that out. And what's left is just I, A naught, which cancels on the top and the bottom. So I1. And what's left over? It's e to the minus plus J. Okay. So now, this is the thing that I have to take all these derivatives with respect to. And I hate this notation now, so let's just remember that this is like J, it's like Aij, but it's the inverse. So it's inverse Aij, Ji, Jj. Maybe that's better, I don't know. And this is with summation notation, so I'm summing over repeated indices. So with that sort of summation in mind, then I can figure out how many sort of elements occur in this sum. So first off, let me rename this A inverse. So it's the inverse matrix. It says elements. And I'm going to call that thing G, because that's what I called it before. Oh, I'll go here. Recall maybe, I forget how we exactly labeled this, but I'm calling these things, A inverses, just G's. Okay, so that's foreshadowing the fact that these are our green functions. So I'm going to call them this from now on. So later on, when you start writing these G's as two-point correlation functions, and we're going to start relating them to the inverse, the inverse arguments of that exponential, or the argument of that exponential is inverse in the original problem, then just remember where this comes from, okay? Basically just comes from this Gaussian. Okay, so next thing we're going to do is Taylor expand that exponential. And when we Taylor expand this exponential, okay, we're just defining the function through its Taylor expansion. We're going to have terms that survive depending on how big n is, small n. Okay. Okay, so what we want is somehow, you know, to drop out these essentially x fields, right? And we want small n of them. So we need the Taylor coefficient that has a product of n of these. And what happens is we're differentiating with respect to j. So we're bringing down, you know, one of these things for every j up top here. But there's two j's occurring in that exponential too. All right, so our expectation value, xi1 ... we'll have the coefficients of the Taylor expansion and its derivative. And in that Taylor expansion, okay, it's like we have these things, these A inverses, and we have these J's, and so I'm going to call these A inverses G's. And we have to be careful because we have these repeated indices, so I'll call them K's. And we have these J fields all the way up to K n. And like I say, every time you pull down, one of these orders in your expansion, you get two J's. And so in order to get the right number of n's, you need the n by 2th order. So that gives you a coefficient that's 1 over n by 2. And 2, there's 1/2 there, so n by 2. So that thing raised to n by 2. So that's a term that survives. But now you have this issue that, like, this is all in this matrix notation. And we have indices here, but we're summing over repeated indices. And so even though this looks, you know, relatively clean, we actually have a really complicated sum that's going on in this expectation value. Okay. And just let me note here. To get nj's, n by 2th, is that a thing? Or okay, so how are these things summed? Basically, we have to match these I indices with these J indices, these K indices, and they're constrained by the G's. Because each G is a matrix, or matrix element, so it has two indices in it. So it's like you're matching pairs of i's with pairs of k's, basically. Yeah. So you can imagine just, imagine you have these n different variables, the indices on these n different variables. I better write an even number here. So let me label those I1, I2, I3. This is n. So this one's n minus 1. And you have to match those. You have to take a pair of those, say this pair, and assign a k index to them. Okay. Well, that's 2 and 3, but let's assign, it's 2 and 3, but let's assign k1, k2 to it. That's one pairing out of n by 2 pairings in one element of that sum. And then you have to pair all of these things. So I don't know. If I do this, and then this one's left, and then this can be whatever, 1, 2, 3, 4, and this one can be 5, 6. And imagine I did that for all n, and I drew this like type of diagram. That's one possible element of that sum. And then you have to do all these different elements. And this gives you all the GIJs. But you see, this constrains the indices and all this product here. Okay? And we take the derivatives of the j's, right? You're still taking the derivatives. All those j terms will go to 0. Okay, or no, 1, sorry. So you have a product of all these g's, and then you have this prefactor out front, this combinatorial prefactor. Okay? Which actually comes, it just comes from the Taylor expansion, but we have a whole bunch of elements in the sum. So what happens is there's all these terms. So what would it be here? So it would be like I1 n minus 1, n minus 1. Let's see. I'm doing it out of k order, but it doesn't matter. So it's I2, I3, and then it'll be like 4 and n, right? Okay, so that's kind of what I drew here, is the indices on the g's. So there's terms in the sum like this, and of course there's n of them, but I only drew 3 of them. But then how many are there? Well, it turns out, which you can convince yourself of, that if there's just a way of figuring out the combinatorial factor of how many possible pairings there are. Okay, so so interchanging indices within pairs gives you a combinatorial factor of 2 to the n over 2, because there's n over 2 pairs, and there's 2 possibilities. It's like, right, that one's simple. And then permuting pairs. Permuting through all possible pairs gives a combinatorial factor of n by 2 factorial. It's funny, right? Because it exactly cancels out the, no? It's not funny? I think it's hilarious. I don't understand why it works. So it exactly cancels out this term out front. So you don't have to worry about this term. These things are all ones. And the only thing that's left over is the product of all your g's with two indices in them. If that's not magic, nothing is. So gi, I don't know what it is. You can write the first element, 3. So you still have a sum, but it's basically this plus all other possible pairings. There's probably a better way to write this. Each pairing only occurs precisely once, actually. That's one thing to remember, but I should have wrote that. So maybe I'll just say sum of pairings. I should have different indices on these pairings. So it's like the sum of all possible ways of arranging J's. Whatever. So that formula doesn't mean that much until you start to do examples. But one thing to note is that that expectation value is the Gaussian expectation value, right? So it's the one with the weight defined that's a Gaussian, and it's the one that is normalized by the Gaussian partition function, if you will. So lots of times we'll be writing this with like a naught, or in this case you would maybe write this with an A. So you'll see both in textbooks. And because it's the Gaussian integral, which makes all this possible. What's this called? That's Wick's theorem. Who's seen Wick's theorem before? Not very many of you. That's my perfect proof of Wick's theorem. Not a flaw in it. You will find better proofs in textbooks. But that's the basic intuition behind it, okay? This chalkboard is a mess. And you have a short amount of time to write that down before it disappears. Okay, so that tells us how to write these like relatively complicated expectation values. It's just products of two-point correlation functions, basically. So, by the way, try it for odd and even n. It'll only work for even n. So we will use this all the time for the rest of the class. It's worth understanding. It's worth doing lots of examples of. So for example, if I wanted the, I don't know, if I had two variables. There's only There's only one possible pairing. I don't know, right? So in terms of these indices, so if I imagine having two nodes that are the indices, I've just connected them. That seems ridiculous to write down, but that's the basic object that you're going to be dealing with for a while now, is this 2-point correlation function, because that's what all those G's are, right? So this is the fundamental object that you have to know how to calculate sort of in whatever theory you're looking at. So once you have that object, and remember this is Gaussian, or this is weighted by just that matrix A.
Sorry, how is that a 2-point correlation function? So the inverse of A is a 2-point correlation function?
That this is by definition.
No, the G though, like the G is related to this, like the inverse of this A operator.
Yeah. So G, the thing I'm calling G, is just. I mean, well, what are you asking? Sorry.
Well, I just have. So you're saying that that A up there is somehow.
Yeah. So A is some matrix or some interactions that are occurring. You know, it's something that's defined by your Hamiltonian, say. Right. So it's like in your Ising model. We're going to do an example right as soon as I'm done this of what this is. But it could be the free propagator of like a free scalar theory, or it could be like the interaction matrix that you're going to figure out in an Ising model or something like that. So it's something that comes from the Hamiltonian, or comes from the action, or comes from the problem. What this is telling you is that A inverse is related to the 2-point correlation function. That's what this is telling you. Yeah. So when there's only one element in that sum, then the 2-point correlation function that Wick's theorem is saying that this thing is equal to the inverse A matrix element, or A ij. So that's the basic result from this. That's the most important result somehow from this. So the 2-point correlation function is related to this inverse matrix. Yeah, that's important to understand. We'll use that all the time now. So I'm still thinking of matrices and discrete variables, but I'll show you the functional integral version next, and then we'll start looking back at the 5-4 theory. Okay, so everything, you know, up to now, this is kind of all just notation, right? All right, so that's the most important one to wrap your head around. And then once you go to higher ordered correlation functions, if you will, or larger numbers of variables in the expectation value, then you start using this sum over all possible pairings. Okay, so remember there's n by 2 elements in each G, or in each pairing. So there's 4. Oh well, that should be a 3. Right, there's 4 of these, so I need 2 G's, and I have to put all possible indices on these things. So 1, 2, 3, 4. That's one element of that sum. 1, 3, 2, 4. Then 1, 4, 2, 3. So that's what I mean when I write all this nonsense. That's what I mean by it. Right, and it's n by 2 because this is what you needed to get a non-zero contribution from the Taylor expansion. And each one of these, which is Aij, you know, for the inverse matrix, is by this relationship, you know, just these 2-point correlation functions. X2, X3. See what I mean? Okay, so that all looks simple until you have repeated indices. I don't know, x4. Then you just have to remember sort of how we came up with this combinatorial sort of, these combinatorial factors here. So this is just 1, 1, 1, 4. So it's like 3, let's see. Again, there's 3 elements in the sum. But you're always pairing 2 of them as 1 and 4, and the other 2 as 1 and 1. So that's all that is. By the way, it helps to think in terms of these like sort of node diagrams. So we'll start to use these quite a bit also. And in this case, when you have 3 repeated fields and then 1 other field, it's like we're connecting. So see up top I had an index 1 and 2. Basically that's what this was, right? And for this example, I have 1 and 4. So how do I connect those? Well, I draw each one of these is like the index. You know, so I have 3 repeated indices. Then I have 1 index here. And so each one of those terms is all different possible ways of connecting those things, right? So that gives something like, I don't know. Do the middle one. Then what? I guess go back. And then the bottom one. Oh, I already did the bottom one. Top one. Bottom one looks like this. So the more you do of this, the more you'll just start thinking in terms of these squiggles and less in terms of all of this, writing out all of these like integrals for these things, which we'll do. So all these calculations, these perturbation type calculations that we're going to do for these expectation values, you'll basically be writing out in terms of these diagrams and all the combinatorial factors. And then at some point, you just got to figure out how to solve, what these integrals are, or what these 2-point correlation functions are. So these are the basic fundamental object needed for Wick's theorem. Everything else is sort of this combinatorial, like, combination of indices. It's weird, right? It's good. So the only thing with all this is I have a discrete number of variables, but I want to use this on a field theory. And in the field theory, I've gone into the continuum. And so we have to sort of just reconcile that picture. So we need to take our Gaussian integration of all these discrete variables and actually turn it into a Gaussian functional integration. But like, essentially nothing changes. So it's just a matter of replacing, this discrete vector of variables x with, say, phi of x or something like that. So it's just a matter of keeping sort of your notation straight. So instead of x with indices, remember this was like x1, x2, x big N. I should have never used x. That's probably why I used y before. Because what happens in the field is x, the vector, I'm going to call it v, just to keep it general, or you could call it phi. if you really want to go right to the field theory. That thing's parameterized by something we call x, which is the spatial coordinate. This is not a spatial coordinate. This is just a number of, like a list of variables, right? So we just have to rewrite. I mean, we can redo the proof that we did last, well, whatever, like 2 weeks ago. But it'll just turn out to give you exactly the same thing, but in these continuum variables. So this variable is going to mean something. It's going to be the value of the field. I don't know why I'm not using phi. Just to be confusing. If it's a scalar field on n lattice sites, then everything's exactly the same as I just did it. But then I can take the continuum limit and just call this whole thing v of x. So the set of all of these n elements is replaced by the field value, and the matrix which has elements, I guess, ij. That matrix is replaced by the operator. And V is one index, so the matrix has to have, x and x prime or something like that. So then your Gaussian integral just completely generalizes to this case where we're dealing with the continuum limit. And then what we're going to have to calculate when we do the 2-point correlation functions and so on, that G is going to be the inverse of this operator, not just the inverse matrix, not just the inverse matrix's elements, right? So just remember, again, sort of the whole goal of this will be to look at this inverse and to use this inverse of this operator to calculate those G12s, or whatever you want to call them. So the Gaussian integral I'll just write it so that you have it. Because we have a functional integral, maybe like this, instead of a sum. Okay, so then I'm going to have I'm not drawing any vectors or any arrows over anything. That's the first element. Oh, and then the j, so that's minus plus this jv. Right. This thing, I don't know, I used to have some 2 pi's, but I can't keep track of that. It still has this prefactor out front, so it's proportional to this. And 1/2, let's see, same integral, but now j inverse j. Okay, so that inverse operator, I mean, it's exactly the same as basically what we just did, but that inverse operator then gets pulled down by the differentiation process, you know, and that inverse operator turns into the thing that we want to calculate for our 2-point green function. Okay, this is basically just a definition. And then by Wick's theorem, this thing is x1, x2 expectation value. And remember, this Wick's theorem only applies for Gaussian averages. So it's the same in the functional integral case. I call them V, but they could be phi's. That would be the 2-point correlation function of the field, right? V is just parameterizing the field value for us. Anything else we need to know? That's the inverse. I guess the inverse, I should have defined it. So for us, it has to be that's right, I need 4 indices, 1, 2. No, I'm integrating over x prime. So this will give me back delta x, x double prime. Yeah, that's useful to know. And I think the only other thing is just like, if we went through the same procedure to derive Wick's theorem, it would apply in this case. There's no difference between the functional integral and all the discrete variable case. So for all these V's, we got the sum over all pairings and the 2-point Green's functions. I need a different index here, J. Okay. So basically what I'm asking you to do is to trust me that what looked like a relatively solid derivation for all this Gaussian integration and stuff just applies in the functional integral case. It's not completely trivial. I mean, if you're a mathy, you might actually work it out, but there's no point. So now we're just going to use this. That's it. We've done all the background work. Now everything else in the course is fun. So the first thing I want to do is look at the simplest phi-4 action and calculate basically that 2-point correlation function. because that's the thing you need. Whenever you calculating correlation functions using Wick's theorem, you're going to draw all these squiggly diagrams and stuff, but you need to know like G1, 2. I want to write down the simplest free scalar field theory. If that makes any sense at all. And I kind of want to imagine that, you know, I'm dealing with the imaginary time path integral because, you know, in all these expectation values, I'm like normalizing by something I identify with like a partition function. So when I write the action, so again, the simplest action if you look back at your notes, we sort of derived this in the free particle case. But all we need is a couple things. So I'm going to have an integral in d-dimensional space. And I think I had written something like this before. We need is phi now. Those are like my v's, but I'm writing my actual field theory. I can't remember if I had a factor of 2 here. I'm going to write my field squared with an r. And then I can have higher order terms. But what higher order terms do is they screw up your Gaussian integration. We'll talk about that in a minute. So I have an imaginary time action. So I'm thinking of something that's, you know, the functional integral has its periodicity and so on. The d dimensions then here, right, are made up of space and imaginary time. And this thing here has been Wick rotated. Okay, so I didn't explicitly derive the imaginary time action, but if you look back like 2 or 3 classes, you'll see the real time action. And you know, I have that Lorentzian metric or whatever you want to call it. I've set the speed of light equals to 1. But the signs for the time and the space direction are different. But once you do a Wick rotation, it's like t goes to minus I tau, right? And so then your time direction picks up the same sign as your space. So then this thing is something just like time derivative and all your space derivatives. And there's no reason to basically treat that coordinate any different. So so your d here is just space plus time. And time is 1. And yeah, so this differentiation variable is just tau and then all your space derivatives. And then, because of that metric, if you want to call it that, like I say, space and time are essentially completely isotropic. So the whole theory is invariant under rotations in this space. So imaginary time versions of actions are called Euclidean quantum field theories.
Okay.
Yep.
What's quantum about this action?
What's not quantum about it?
All right.
So remember how it was derived, basically, right? The you wrote coherent states, right? You operated on the coherent states to get matrix elements, and instead of, you've thrown away the operators, but now you've gained an extra dimension. So what's basically quantum about it is that extra dimension. Yeah. And we integrated out the Berry phase in this case. Okay? So that's the other thing that's quantum that you have to worry about. But in the single particle path integral, when we wrote in P and X, right, we could integrate out that IPX term or whatever it was, IP.x. And so that's the other piece that's really quantum. And so I think it's good to wonder, or it's good to do some soul searching about, what's really quantum about this, because that tells you what's really quantum about anything. Yeah, it's deep. But it's true. So you can imagine doing let's think back to the first example you did in this class, the transverse field Ising model. Okay, the transverse field Ising model is obviously quantum mechanical. It has that sigma x operator. Right. The first thing we did when we took the transverse field Ising model and we wrote it as a d plus one dimensional classical Ising model, we threw away, it seemed, a bunch of the quantum mechanics in favor of this extra dimension. But that extra dimension was really complicated. Like the couplings in imaginary time weren't the same couplings as the couplings in real space. And that's because you had that sigma x operator in there. That sigma x operator is different than the sigma z. It has like the transverse field in front of it and stuff, right? So the transverse field gave you the values of the couplings in that extra dimension. What we've done here is we've taken that extra dimension and we've made the couplings the same as the spatial dimensions. Okay, so that's something that's not completely valid, maybe for all the entire phase diagram of the transverse field Ising model. So this quantum field theory isn't general enough to describe, all the phases that occur in quantum models like that. What it does describe, which I haven't justified, is the quantum critical point between the paramagnet and the ferromagnet. So the quantum critical point that you derived on your assignment, that's h over j equals 1. If you're sitting right at that quantum critical point, that's when this theory becomes 100% valid. And that's basically the subject of 705. That 705 tells you why this theory is valid to describe that quantum critical point. Okay? And basically it's because, well, I'll show you maybe roughly why, but that's because the correlation length goes to infinity at the quantum critical point. And if you derive the coarse graining through the renormalization group, you find exactly the same Lorentz invariant field theory.
Ready?
Yep.
Comments about the d-dimensional rotational invariance. Like the tau dimension is periodic, right? It's not.
True.
There's a clear difference between still the time direction and the spatial direction.
So one's periodic, but infinite at zero temperature,
Right.
and one's just infinite.
Okay.
Yeah. Then no, it's true. You should be careful with that. So this is like the most extreme. Everything's, when you start writing stuff like this, you're in the continuum, you're in infinite space and in all dimensions, yeah. But yeah, it's good to keep that in mind. So, and if you're disturbed by how easily I just scratch some action on a chalkboard, well, then you know what it's like to be like a field theorist. You're just throwing random stuff up on the chalkboard based on symmetries and vague ideas of boundary conditions and stuff. So this is it. This is your first like real field theory calculation.
Seems like a good life.
You're telling me. So what do I want to do? What did I do? I wrote this action. That was fun. Okay, so, oh yeah, I'm calculating the propagator. That's what I'm doing. So, okay, so in order, I only know how to do it in Fourier space. So we're going to Fourier transform everything. Okay, so I have fields, and I'm treating all my coordinates the same. You can call them x0, x1, x2, which people do in Euclidean theories. The time is just some other, right? I'm setting h bar equals to 1 here. So I'm going to take my fields and substitute in fields written in momentum space. And remember that this is a different object than this. Sometimes people write this with like a tilde over top or something like that. Just so you remember that it's not the same function, just with p substituted into it. It's the Fourier transform field, right? It's a different function. I don't know if this normalization's right. I forget. I think in field theory, the transform has 1 over 2 pi, and the inverse transform has just 1. But it's too late. Yeah. I'm going to throw all those 2 pi's away. So when you want to write these things in Fourier space, just substitute in the fields right into that action. I guess I'll do it to kill some time. Actually, it's a useful skill to have. Okay, so all the terms in the action, so phi squared. There's 2 of these things. And we've done these before with sums, I think. Yeah, when we did Matsubara frequencies, remember we did sums? So the only thing you have now is, instead of sums, you have integrals. And just like when you had a square of 2 terms that have a sum in it, you have to have different indices on your sums, k and k prime. You have to have p and p prime here. dp prime. And so the way this always works, it's always the same trick. You take this integral. Let's just do it in 1D. Yeah. Let's do everything in 1D. So let's imagine I just have one. I mean, it doesn't. You just have d one-dimensional things here. But if I have my integral over x, I just bring that in and I use the Dirac delta function to get rid of that integral, and then everything will be written in p space. I'm not presuming you don't know how to do a Fourier transform. I just think it's good to have practice. Maybe it's good for me to have practice. So you want to phi p prime e to the I x. When we did Matsubara frequencies, everything lined up so that we had something like, I don't know, it would be k minus k prime or something like that. But here it's a plus. And so that's why you always get, for your 2 fields, you'll always get a p and a minus p when you do this type of thing. So you always see p and minus p after these Fourier transforms. It's just because of, that's how the phi squared transforms. And so once you bring in the, once you bring in the integral over x, so you want the delta function, what am I integrating over, p or x? X, so I want this to be p. Yeah, now I'm worried about that normalization. Oh well. So, oh well, that works for what I have over there. Okay, great. So it means that that integral from minus infinity to infinity dx phi squared. So the one-dimensional version of the second term that's proportional to r. Gives me p, yeah, and so this is like p plus p prime is equal to 0, so this one has to be minus p. Okay. Yeah, those will matter at some point, those minus signs. The derivative one's a bit more interesting. So the first term here, you actually have to take a derivative in the exponential. You'll pull down that imaginary number. Everything's squared. So all you have to worry about is a minus sign there. All right, I'll just sketch this real quick. So if I had the x derivative of one field component, I guess that's the thing that'll tell you what's going on. You just substitute in you just substitute in this value for phi of x. I would do it like this. I would take the derivative and then square it, so that'll pull out the IP. So I've just pulled the I out front. So now I'm going to do the same thing. I'm squaring this thing, so I'm going to put two different indices, if you will, like a p and a p prime. But then I'm going to use the Dirac delta function, right, with this integral here. But what happens is, so I'll get the fields, like a field of p and a field of minus p. But then I'll also have a p and a minus p coming from the argument of the integrand there. Wish I could fit that in. I hate erasing. Okay, so you see what's going to happen. You're squaring it, you're getting two i's, which give you a -1, but you're also getting a -1 there. Okay, so. And you can keep these things in order. You don't have to assume they commute. I, x, p plus p prime. Because that'll give you a nice form for Okay, so at -1 out front. I have the field. I have P. I have minus P. I have the field at minus P. Did I forget anything? That's probably it. So that's your minus signs that cancel. Yeah, that seemed really boring, but at some point, you really wish you remembered this. So the main thing to remember is the derivatives basically bring down powers of the momentum.
Sorry, Roger. Did you say these things did not commute? Or did
I said you don't have to assume they commute. Just leave them in the order. You know, this is a scalar,
yeah, right.
so it doesn't matter. But people will just write them. You know, if you have some more complicated thing that's not a scalar, it's just nice to keep them in this order. So now I'm writing my action in momentum space. That's what I'm doing. And that's going to give me the Gaussian propagator. Integral. Let's write in d dimensions. But then my p's are vectors. And phi. Okay, so 1p or p squared from the derivatives, and then the other thing's just phi, just r. And I pulled the factor 1/2 out front. You'll see that this is like, this is the simplest momentum space free scalar action you can write down. That r, well, I'll tell you about it some other time, but that r is just the mass of a Klein-Gordon field. So people will write an m or an m squared here, I forget. Yeah, probably m squared. So you'll just see p squared plus m squared sometimes. And at r, which is just, remember, it's just a parameter that I absorbed all these other factors into and blah, blah, blah. You can imagine it coming from the microscopics. But you can also, I'll show you when we do the saddle point approximation, you can also just basically show that this thing is equal to the Klein-Gordon equation. And then this would be the field theory for a relativistic particle of mass, m equals m squared equals r, yeah. So when people are saying massive or massless theories, they're basically telling you the value of this thing, whether or not it's 0 or non-zero. But I want to do the 2-point correlation function. Let's do that. So it's defined as, P and minus P. And it's, it's Gaussian weighted here if you want. But that thing's the green function, which is the basic object that you need to calculate for all of these more complicated expectation values and so on. So by definition, that thing is, the inverse operator, remember? Which is just this thing. This is your like J. This is your A inverse. This is your J. This is sorry, your A, and this is your J. So you just need the inverse of that operator. And that's what your momentum space G is. So the nice thing about momentum space is it just gives you a nice form to write G in terms of p squared plus r. So that's cool, but it's not very maybe instructive if we're used to thinking of fields in real space. So let's just transform it back, Fourier transform it back into real space. So some position x and x prime, and it's often convention to just set x prime to 0 or something like that. So I just want a function that depends on the distance of between some field at the origin and some field out at position x. So the d-dimensional integral expression for this just comes from the Fourier transform again. And in different, the dimensionality of this Fourier transform actually really affects your results. So 1D, 2D, 3D, it all makes a big difference. Let's just look at the one-dimensional case. Okay, so in 1D, this Fourier transform is really simple. But what's going on is we have a p squared plus r in the numerator there. So we can use complex analysis in a very simple way to do the one-dimensional integral. So let me write this thing as p. I have to plus or minus it, so that's why I need it. Oh, that's why they use m squared. Okay, so the p integral has simple poles. I used to have a Russian prof that had an awesome joke about simple poles in a complex paint, but it's like racist, so I can't say it. So you have these simple poles here, and you're just calculating the well, don't imagine the joke. Stop it. This is back in the old days. It was like the 90s. So you just take this. You can just do this integral with this contour. So it's p is what gets eliminated. And that's it. So what this shows you is that if you have a field at point, phi 0, some position in the continuum, and you have some other field at some position x, so in one dimension anyway, and you're sort of asking about how correlated are those fields. That's what you're asking with this green function. So you can imagine those fields might describe the averaged order parameter of a spin in your Ising model. So you have a spin at some lattice site, but you're in some long wavelength limit where the lattice barely matters, and you're very far away, and you're asking how are our spins correlated. And so in 0 dimension, what happens is you just get an exponential decay of this correlation. What dimension did I say? 1 dimension. You just get an exponential decay of these correlations. And whenever you have an exponential envelope, like whenever you have this form, you can just ascribe a length scale with the constant, right? Or it's 1 over that thing. So that's how you ascribe a length scale in any of these theories. So it would be, so it's minus, right? So then it's 1 over root r. So this is the correlation length is like the fundamental object that you deal with in 705. It's the thing which determines whether or not you're at a critical point, whether you're long-range ordered or short-range ordered or so on. You can have algebraic correlations that don't have this exponential form.
Question with respect to that. So if I set x to 0, then correlation function at large distances is a constant. So does that mean that there's no long-range order and hence there's no quantum phase transition?
If x is 0, sorry?
If x is 0.
If x is 0 means you're asking about the correlation of a field with itself. It should be 1.
Yeah, okay.
Yeah.
So if you set x to infinity, right?
Yeah.
You should expect that if there's a phase transition, then it should go like algebraic to decay.
Yeah, so there's a different form for that, basically.
So the question is whether, if I look at this form,
Mhm.
I see that it decays, goes to 0 at infinite x. Does this mean that the Ising model in 1D does not have a phase transition at 0 temperature, right?
It basically means, so 0 temperature you have to be careful. But it basically means that, yeah, so it's the argument for why or why not phase transitions exist, yeah. So okay, it's a little bit more complicated when you think about how this mass is behaving in certain theories. So actually, in this case, you only get a critical theory when this mass is 0, okay? So the free scalar theory in this dimension is sort of a little, it's a little unique. I wouldn't say this is sort of absolutely typical. The exponential behavior is typical. If you go to 1 higher dimension, then everything you're saying is basically true. You'll have a regime that's exponential decay. Then you go to something that's critical, that you'll actually see some sort of algebraic decay as you tune parameters, essentially, in the system. What happens here is the only thing you can tune is the mass, okay, if we want to call it the mass. And the only other interesting regime of this field theory is when that mass is equal to 0. And then your correlations blow up. And that requires some interpretation. But like one way to interpret that is that you only have a critical theory, if you will, when that mass is 0. Okay, but we'll talk about that more when we talk about symmetry breaking and so on. Okay, so if you go to higher dimensions, I encourage you to do it. Then that form becomes more complicated. It's like less pathological, if you will, and especially in its dependence on the mass. You'll see, I don't know, there's some Bessel functions or something that come out of this. So I don't know. Look in a book. I could barely do this complex thing here, so I'm not doing anything in higher dimensions. So you're seeing this sort of emergence of critical phenomena and critical theories come out of this action. The idea of a correlation length, okay, the idea that there's a characteristic length scale associated with systems, and again, even though the action isn't like derived directly microscopically, it's definitely motivated by microscopic derivations, and you'll do the d-dimensional Ising model on the next assignment. You'll derive this field theory right from the Ising model. So
when you say critical theories, what does that mean? That means correlation lengths go infinity? Or?
Yeah, so typically, this is 705. So a critical system is when the correlation length goes to infinity. That's typically the definition. So it means that there's a characteristic length scale. And so again, you can imagine that the characteristic length scale might be these like minority clusters in your Ising model. So if you imagine doing this like perturbation expansion, you get these minority spin down clusters. Those things have a length scale. I mean, they have many different length scales, but this is like the average length scale of those clusters. And as you approach the phase transition, like the phase transition in, say, the 2D Ising model, that length scale of those clusters goes to the size of the system. That's, remember, it's like I argued it's like a percolation thing with this Peierls argument. Those minority clusters will become no longer the minority. They'll become as important as the majority clusters. And so then your length scale is essentially gone to infinity or gone to the system size.
And that's when you get into this, what you call critical regime.
Yeah. And the field theory, if we did the proper field theory for that Ising model, this is the correlation length that would emerge. You would get some form like this in 2D. You would get something that you can define as the correlation length. And you would basically see that thing diverges at the critical temperature.
So this is fine for second order phase transition, right? Where correlation then
Yep.
is infinity, but what about first order? Can you use?
Yeah, so first order phase transitions. So number one, you can put a term in your action that gives you a first order transition. So we can talk about that if you want. What happens is you have a discontinuity. So your correlation length grows, 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 and then all of a sudden it's finite, but you flip into the other phase. That's a first order transition. So I can write an action that I'll do it when I'm going to do a bit of perturbation theory, and then we'll go back and look at this question. So I can write an action that gives me a first order transition where this thing doesn't diverge. But also in a real system, like if you just have a real experimental system or a real infinite many-body system, you can always have fluctuations and higher order terms that you're not really sure of that can induce first order behavior. So remember, these are like the simplest actions, derived by symmetry arguments. In a real system that you guys will see experimentally or numerically or something like that, you'll often see first order phase transitions just come out because there's fluctuations that you haven't accounted for in the actions. But so those are less interesting first order transitions in a theoretical sense, because when this correlation length goes to infinity, that's when you get the renormalization group and you get all this kind of interesting critical phenomena that you study in 705. So that's what they call critical points. And this could be the theory of a quantum critical point in d+1 dimensions. Okay, we'll talk about that next time. Your homework 3 is due next time. Your homework 1's up here. I'm almost done marking homework 2. They don't give me a TA, so I'm just marking based on weight. And either this week or next week, I'll hand out your computational assignment. That's worth 20% of your grade. That'll give you no hints about how to do, because no, I'll give you basically an exact diagonalization code, and we'll build up a numerical solution to some 1D problems.